Okay, here's the deal. A lot of people have said that using the Laplace transforms to solve differential equations is lazy since you just memorize the inverses. I can see where they're coming from, but we also memorize elementary derivatives, integrals, etc. So I don't really see an issue with it, but just to prove a point, I'm going to demonstrate that you can also derive the Laplace inverse of a function using contour integration. So, without further ado, let's get started. Blah blah blah. Let's get started. So, first of all, we're going to be using this formula here because it's quite a nice formula. Let's get started. So, for this example, we're going to be taking the Laplace inverse of 1 over s. Plug it into the formula, we get 1 over 2 pi I integral c minus I infinity to c plus I infinity e to the st f of s ds. What is c? C is, well, essentially, for this function here, there is a singularity at s equals 0. And c is any constant which is greater than the real part of all of the singularities of this f of s function. So here the real part of 0 is 0, so c can be any number greater than 0. We're going to be using 1 today because it's quite nice, quite simple. This is just 1 over 2 pi I integral of 1 minus I infinity to 1 plus I infinity e to the st f of s ds. Now, f of s is 1 over s, so this is just 1 over 2 pi I integral of 1 minus I infinity to 1 plus I infinity e to the st ds over s. And we can do a substitution, and when we substitute, z is equal to, 1 plus iz is equal to s. We get I dz is equal to ds. Carrying out this substitution, we can bring the I to the front of the integral to get 1 over 2 pi integral from minus infinity to infinity of e to the t 1 plus iz over 1 plus iz dz. Now we can do a few things. We can bring this e to the t out to the front from this part here, and we can also bring an I out to the front, so let's do that now. E to the t over 2 pi I integral minus infinity to infinity of e to the itz over z minus I, because 1 divided by I is just minus I dz. Now we can draw a pretty picture from our real imaginary axes. Draw the singularity at I and draw a nice pretty semicircular contour in which we're going to integrate over. We call this arc gamma and this straight line I, and when we limit r goes into infinity, this I just becomes this original integral. And we'll call the whole curve C. Now it's worth noting that the integral over C is equal to the integral over I plus the integral over gamma. Let's start by analysing this integral over gamma. We can parameterize it by gamma of t is equal to r e to the it, with t running from 0 to pi. Right, that gives us a semicircle. And doing such, we can use Jordan's lemma and notice that the coefficient of this complex exponential is just 1, and on the bottom we have a linear term, meaning that by Jordan's lemma this will go to 0, which is quite nice. We get that this contour integral is just equal to the original integral. So, carrying forward, we get that this whole thing must equal e to the t over 2 pi I contour integral over c of e to the I t z over 1 plus I z. Sorry, we took out that factor. Z minus I dz. Now we can use Cauchy's residue theorem to evaluate this contour integral. You could also use Cauchy's integral formula or Cauchy's differentiation formula. Either way, you'll get the same answer. We get e to the t over 2 pi I times 2 pi I sum of residues. There's only one residue, and it's the residue at z equals I. So this is equal to e to the t, cancelling these two terms, times the limit as z approaches I of e to the I t z and this is quite simple to evaluate. We just see that this is equal to e to the t times e to the minus t, which goes to 1. Therefore, the Laplace inverse of 1 over s is equal to 1. There we go. There's the answer, solved. Taking the Laplace transform of 1 obviously yields 1 over s, and I think it's quite nice to look at this method, see exactly what is going on, and just appreciate that, yeah, you could just look at a table of inverse Laplace transforms, or you could do the work, go through it, and derive the inverses for yourself using integration. And quite nice integration most of the time. 9 times out of 10, Jordan's lemma will do the work for you when you draw this semicircular contour. Sometimes it's a bit more tricky. I will go over other cases in other videos. But for now, I hope that this video inspires you to go out and play with this idea yourself, because it is quite powerful. That's it for now. See ya!